Online. Okay, so welcome to the third lecture of Walter van Suijlekom in ISI Kolkata. Today he is going to talk on second quantization of spectral geometry, entropy, and spectral action. Walter.
Okay, thank you. Yeah, so third lecture I will move into the quantum world. Realizing, of course, that you may not all be quantum physicists, so you have to be a little bit easy on that. So let's start from where we are. So I mean, not physically, but okay. So yesterday we were talking about spectral triples and how to fluctuate, and so maybe a very nice example that sort of puts several of the examples I talked about before together is the following. So it's smooth functions from M, but not taking values in the complex numbers as usual. They actually take values in two components, like this C plus C, but now I put C plus H, whereas H is the quaternions. So it means my coordinates are something like a combination of a point and Q of a point. So P is in M, and this combines this classical geometry of M with this kind of more non-commutative structure and this two-point structure that we had. And so this is an element in C plus H. But you could just think about them as coordinates, except that they are non-commutative. But it's a nice perspective on these kind of things. So that's the algebra. Then I have, as I said, my spinor bundle, which I actually tensor with a representation space for C plus H. And I take the simplest one I can imagine, which is C3. So that this acts here by pointwise multiplication. So if this is an element in the algebra, then A on such a section with the vector, let me write it actually as, let's see, just like that. So then it will be at the point P, because this is still a section, it will be ZP, so S of P tensor, and then ZP QP in a matrix acting on this V. Yeah. This is a sort of the way to kind of try to put a formula connected to this, and then the Dirac operator is a combination of dm acting on this with something acting on this C3, and that's like our finite size df. I call it f for finite, where this is the 0 and the C. So I put them here, yeah. And now I have to be a little bit more zeros to add, but I just have this complex number C that I had before. And it's now, there was one more 0 because it's quaternion, so there's more variable. So that's a 3 matrix acting on this C3. And for this we can compute the inner fluctuations. So we can compute omega 1 d of A for this spectral triple, and it gives a new d prime, where actually, so what you find is that this C and the H, they will generate an entry in DM, which is not acting times 1 anymore. It actually has some component that acts. And I will not spell out the full formula that you can find in my book, for instance, or in other references. So it contains something of this type. It's a 1 form. So let me write this as like this. And there's a 2x2 block corresponding to these quaternions. Because even though I started with dm just being the Dirac operator, I have these coordinates which are non-commutative. So if I compute these commutators, these 1 forms, it will contain such an entry for every mu that I have available, for every dimension. And the computation I did before, this I can also do again. It will actually lead to this, where these phi1 and phi2 are C values.
So these are in the space of what forms for D prime, or
no? This is in this one for D,
okay.
And then this means that D prime, which is D plus omega, contains these terms. So this is it's omega contains these kind of contributions. And I write contains because I didn't spell out the full detail, but that this is more or less what you get when you compute this omega 1dA.
So these lie in so these two matrices lie where exactly?
Yeah. Okay. So if you force me to write it, I will. So omega is this plus, and this is 1 tensor. And the 1 is actually, I'm cheating a little bit because I didn't talk about gradings. So this 1 should actually be a grading, but other than that, because I will not use it anyways, I'll jump over that. And even this is actually better written like this, because the phi1 and the phi2, they're in C, but at each point P. And the same here. So a mu of P, that's an element in, well, there's actually an R, because omega should be real, self-adjoint. And the same for the omega mu's. This will actually lie in SU2, the Lie algebra SU2. So at each point, I have this expression. Now, if you're a physicist, and you're very happy about this, because this is a U1 gauge field and an SU2 gauge field, which is coming only out of computing this omega 1dA, where these are the Higgs fields that you're used to. They vary, they're now really fields depending on P, and they vary over the manifold M, and then they do precisely what you want from a Higgs field. So they are in the right representation of SU2 and so on. So that's what comes out of the computation, and it's always the same computation of computing AJ, D, BJ, summing. And the AJs and the BJs, they're of this type, and the D is of this type, and then you just do the computation, and then this is what you find. So and that's in physics called the electroweak theory, where this is the Higgs field, and the W is the weak interaction, so it's the W boson, which is actually experimentally observed a long time ago. The A mu is the boson corresponding to hypercharge. So there's a combination of A mu and W mu 3, which is the boson, and the other one is the Z boson. Sorry, the first one is the photon, the other one is the Z boson. But I expect that not many of you are fluent in particle physics jargon, so I will only use this as a sort of an indicator of these particle physics models. Because what it does tell us is that so we get some kind of some physics out of this, but it's also maybe limited to what we call a one particle level. Which means that, so you could determine such a, so you take a psi in H, and you can look at the so-called Dirac equation, which is this one. It's the Dirac equation because, or actually that's why we call this the Dirac operator, because it was the equation that was found by Dirac, as I explained in the first lecture, to make sense of something which is more relativistic, so compatible with space-time symmetries. So he wrote this formula and identified the right ingredients, which we already developed. And then it tells me how a fermion, this fermion, psi, propagates in M. Of this fermion in M. So it's something like between 2 points, or P and P prime. It's just telling me how would that actually, what would be the propagation of this this psi that describes for me the fermion. And that's actually one particle, because nothing will happen along the way. So it will just propagate, and it will not interact with anything. It will just move, keep moving. It will never stop, but it will also not do anything, which in practice is not what happens. I mean, there's a lot of interactions with all kinds of other material or other matter or other fermions, which we should somehow try to incorporate, and that's actually one of the challenges of the field as we stand. And the second quantization is only the first step to try to identify what are the right what is the mathematical formalism to get from one particle to multi-particles. Another thing is, so I already said that there's nothing happening along the way, so this means that dynamics is missing, and that's also something we try to kind of tackle. And we try to do both at the same time. So very ambitious, of course, to try that, but of course the way I phrased it is it's that it will actually work. So let's do that. So we and I need a little bit of formalism, which is about second quantization. And so for more details, there's a very nice reference. So I will try to describe it in as good as I can, but otherwise you may refer to this this what we call the Green Book, which is the Elements of Noncommutative Geometry. I don't know if you know that, but it's Garcia, Bondia, Varilli, and Figueroa. It's called Elements in the sense of Euclid's elements, but not of geometry, but of noncommutative geometry. And they have a chapter on Clifford algebras, and that actually continues into infinite dimensional Clifford algebras, and everything is sort of spelled out. Actually, what I will use is also explained there. So, so let's first look at the central object where everything is taking place, which is the Hilbert space H, and we start replacing that. Actually, that's describing this one particle. And this we have to sort of do better and describe something which is multi-particle. And so we need some kind of quantization procedure. And the way to go from a vector space to something which is like non-commutative, we have already seen that, which are these Clifford algebras. So we'll actually do that in the same way as I did some of these Clifford algebras. So H comes with a an inner product, of course. So it means it's a vector space, so with an inner product. And if I forget for the moment that it's infinite dimensional, I will look at the underlying real vector space. So what you can do is, so H is a complex vector space, but like C or C2, that's also a real vector space. Okay, it's just twice the dimension, and in infinite dimensions you don't even notice. But this is the underlying real vector space, and that has actually a metric on it, and which is given by this. But it's a metric because the conjugate linearity you don't see because it's just over real now. So this is the metric. So this means I have a vector space V and a metric G, which is very much the way I started in the first place, right? Because I had this, there I talked about the manifold, but the metric is really, the remaining metric was really a metric on the tangent bundle. So in this case, I have this combination of a vector space plus a metric, or like a remaining metric or an inner product. The quadratic form, which is equivalent actually. That's also nice, by the way. Q of V, the quadratic form, which is G dV. That's the same, so you can move between the two. There's a way to kind of polarize this to get G of V, W, but it requires a few lines thinking about what quadratic form means. So, and this is all linear now over R. And it is then possible to define a Clifford algebra for such a V. So I was looking in dimension 2, so R2, and you take the standard inner product, Euclidean. So that's an example. This is the general definition of this thing. So you take R2, so what do I have? I mean, the construction is linear, so I can take the basis vectors E1 and E2. So they're the generators. Cliff of this R2. With the relation that, and now I just write what I have. Of course, I should have written relations because the V and W run all over the vector space V. So there's many relations, but linearity, which you can see from this, makes it condense actually to, in this case, only E1 and E2. But then I have a few of them. So I have E1 times E1 plus E1 times E1. So that's E1 times E1. This should be twice, but that is cancelled by this division here already. The inner product of E1 with itself, so that's 1. and this is also E2, E2, and then E1, E2, plus E2, E1, this should be 0. So this is the first example I was talking about Tuesday, right? So this is the fact that I have something that squares to 1, maybe I had -1, but apart from that it's the same thing. And this is the anti-commutation. So I can try to represent them as matrices. I mean, this is a representation, so this is more an abstract definition of the Clifford algebra. So they're represented as something like this, and E2 maybe something like I minus I. And if I take their product, I get something which is something like I minus I. And if I take their well, if I continue, then I see that actually I can generate everything I need, and I get to some algebra, which is in this case M2 of R, if I'm not mistaken. M2 of sorry, this is H, right? Yeah. This I should. Well, this I will check just to be sure. It's a danger of doing something on the fly. So this is M2 of R. And the way to, yeah. Actually, because, I mean, you may see this represented as complex matrices, but it's not necessary. I could have done this with 1 minus 1, for instance. Then it also anti-commutes with this. So maybe that's a good hint. I mean, the representation was complex of this M2R, but the algebra itself is like that. And in fact, you can realize it as follows. And then if you take products, so for instance, the product of E1, E2, that has a 1 minus 1. And if you take it square, you get 1, 1. So you more or less get all the matrix coefficients, the basis for the matrices independently. So the thing I wrote was a complex representation of this real algebra, but now you see it actually as M2 of R. So that's a better choice of Pauli matrices for this. Okay, is it clear? So, and this continues, okay, so there's all lists of all Clifford algebras of all kinds of structures, of all kinds of metrics, G. But for that I would like to refer to that book, for instance, or my book. There's many other places where this is spelled out. And the good news is that there's a periodicity, period 8. So this means you only have to compute 8 of these. And then it starts, well, it's up to Morita equivalence, but then at least you know that after 8, it's a tensor product of the thing, for instance, happening in n is equal to 1, times some matrix algebra. So you know exactly what to do, and you can just limit yourself to the dimension 1 until 8. Okay, so this we do, but now for HR, which is infinite dimensional. So there's a subtlety is that we have to take, actually it's like a direct limit construction, which we built from the inside, doing all finite dimensional subspaces of V, doing that construction, and then take the direct limit construction. So that's what we get. So we call that C, which is Cliff. And now for that specific V, with the thing which is given from the Hilbert space. So that's our Clifford algebra. And what we also do is, for convenience, we complexify it. Because otherwise, I would have to talk about real C-star algebras, which is much more challenging. So, and in fact, this is already sufficient to describe what we want. So this is the algebra that we get from this procedure of what is called second quantization. So and so let's look a little bit at its properties. I mean, there's so let's look at representation theory to start with. So what are the irreducible representations of this? Now what you can do is, so here I made the step from H to HR, forgetting about the complex structure. But what I will do now is I will introduce a complex structure on V. So you take I, an orthogonal, so it's orthogonal with respect to that metric, complex structure on V. Which is not necessarily the one coming from H that I started with, which has an I, of course. So there's in particular a complex structure on the vector space, which is the I, which still acts there because it was just. So this gives me VI, a complex vector space, and I give an example of such an I in a moment. And actually, I let I vary, and then I can have a representation, gamma I. And the gamma is, of course, the one, the gamma mu's, it should reflect the same thing. Two linear operators on this, where this is the exterior product of the vector space. So these are the exterior powers. Algebra of V, I, and how does V act? So in physics you would say creation and annihilation operators. It's creating a V and it's annihilating a vector V, and that really means something about particles that are being created or being annihilated. Where the AI star V is the simplest to write, it's just V wedge. So it just adds V wedge and then whatever you had. So that's an operator on this exterior algebra. It's just the exterior product with the vector V. And the AI is the adjoint of that. So even though I put the star on the other, AI is the adjoint. So AI is the adjoint of AI star V. So it annihilates a vector V, and you can write it down explicitly as well. It's like the inner product with this vector V, but then over all the entries in the wedge because of antisymmetry. So that's why this is more complicated to write, and this is easier because the wedge has this nice property of antisymmetrizing. Okay. That's a representation, and actually, little lemma is irreducible for all complex structures I. And that's a lemma we show. So actually, I should also indicate this, as this is work with Shamsuddin Khan about 5 years ago. That is in CMP in I think 2018, where all these results and this construction has been done. So irreducibility follows from a Schur's lemma. So it's very similar to what you're used to in Lie groups or discrete groups or Lie algebras. Okay, so let's see what more can we move from V to this well, first of all, this algebra, and maybe then secondly to this Hilbert space. So notice that this is an exterior algebra of an infinite dimensional, actually a Hilbert space. So again, that's a Hilbert space, which is called the Fock space in physics. Fock space. But it's really just this one. And the inner product is just what you do with exterior algebras is that you take the inner product for each entry in the between the wedges. And the wedge then again takes care of all the anti-symmetrization. So it's very convenient to write, but for that I really refer to that book.
So this sort of construction also appears in Bott periodicity, right? Bott periodicity for, let's say, infinite dimension or something. In KK theoretic group.
You use these Clifford algebras to indicate.
This kind of thing.
I don't know which one you have in mind. I mean, for Bott period.
Yeah, this kind of construction of Clifford algebra, like you start with this Hilbert space and.
Yeah. So what happens is.
Paper by Higgs and Kasparov, so they do similar kind of stuff.
Okay. Yeah.
So this is just the antisymmetric part of the Fock space.
Yeah, this is the.
It's an antisymmetric or fermionic
Yeah.
Fock.
Yeah.
Yeah.
There's also a bosonic or symmetric counterpart, also the free Fock.
Yeah. So if you like indeed the Fock as a whole, Fock space, then it contains fermionic and bosonic or antisymmetric and fully symmetric.
And second question is that, so like what is the complex structure involved?
Here. It's a good question because I said this is the adjoint of AI star. And here you don't see it, but you will see it in the adjoint.
So the inner product on the wedge VI depends on the complex structure.
Yeah, because I acts as I here. So if you write an inner product, it will have to respect the linearity is now, so the antilinearity or the sesquilinearity of the inner product is with respect to this I.
Okay.
So maybe it's good to say this I acts on VI as I, which that's the only thing you have to get used to with complex structures, and that's different from what I started with. So I have H, I know what I does, but now I change the way I does because it will act as capital I, which may be completely different. And it will be in a moment, and I will give a nice example which will actually make things very computable if you think about Dirac operators and so on. But this is where, if you think about inner products, that really comes into play with the adjoint, of course, where you have to take the other component into account. So here you would see a difference. And there's indeed explicit formulas for that in this book. All right. So suppose we have a map, so orthogonal, sorry, on V. So V is always now my HR, okay? So this I will stick with. It's only at the left that I have V, a general vector space, each HR. So that will induce an automorphism. So this is, of course, linear and orthogonal. Map like this, an automorphism, where it maps gamma IV. So I'm looking at its representation to gamma I TV. So so maybe a note, if you think about orthogonal maps, then it's clear that this will actually be respected by that, because I can, if I act with t here, I should be able to act here as well. But this is just a number, so I should be careful in making sure that it can be put in front of the v there. And that's because orthogonality allows me to do that. In its representation, I found the following. So this is of course a capital T. Sorry. So you find that the gamma IV is mapped into this one, and then you may wonder, okay, can I somehow make this even more concrete? Because I don't really know what this is, because it's yet another representation of a vector in the Clifford or an element in the Clifford algebra. So you may wonder, can I represent this, sort of induce it by something that acts on the Fock space? So is there a lift of this map, this automorphism, to the wedge VI? So it's again similar to what we were discussing over coffee, is that that you have this automorphism, which is given to you, but actually you need something better than that, which is the lift to the Fock space, which implements that automorphism. Now that's not always possible. There are obstructions to this, and they're very nice also to try to understand, especially in this context, because this is something that happens classically. But here we're talking about something which is like in the quantized case. So you should be able to do that under some conditions, and at least one which will work is if U is unitary on VI. Because then I can introduce a wedge. Sorry. So this is a wedge U. So this is the induced operator. UVN, like this. So this wedge construction actually works for all kinds of maps. So well, the wedge of a map is then acting in each of the components, actually turning the wedge into a functor, because I have linear maps between vector spaces. So that's my T's, the maps T. And as long as they at least respect the G, the metric on there, I can wedge everything, and then I have my induced maps on the Fock space. So that's this notation acting on a wedge VI. Then you can check that this happens, and this is not very difficult. That this is actually implementing that unitary. This automorphism given by this unitary is implemented by conjugating with this wedge U. And this is, you can even, while I'm erasing that, you can check that that works, because I have the formulas there. And you just see what happens with the wedge that appears in this thing here. The only thing that happens is that that picks up a U. So it's like U star is acting on each of these, on these wedges. And then I wedge it with V, and then I apply my wedge U again, which again plus all the U's. And the only thing that happens is that the difference lies in the first wedged UV vector. And this actually implies, because I can also take its adjoint, that the gamma I V that I had corresponds to gamma I UV. So that's exactly what I want. So this is very good. So I'm in good shape in that sense. I can find operators on the Fock space that implement the automorphisms that are given by or induced by unitaries on the classical space, the one particle space. Okay, so then there is a proposition, because now we are in, well, we have a representation of the Clifford algebra on some Hilbert space, and we of course need to think still about the operator D that we had in the first place. So maybe before, let me look at D, and let me put it into this this form, actually a unitary. So D, it actually gives rise to e to the I td. And this e to the I td, that's an operator, of course, on the Hilbert space I started with, but it's actually it induces an automorphism on the Clifford algebra. Bye.
This is what you want?
Yeah.
So you want to find the D so that this...
Now D will always do that.
Huh?
The D I started with will always do this. So my D that I had, the given D, will induce, so yields a unitary e to the ITD, which will induce an automorphism of Cliff, which is given as follows. So it's sigma t so I call it sigma t, which is gamma I e to the I t d v. So it's my unitary that I had in the previous discussion. So the spectral triple I started with gives preferred unitary, which is this e to the ITD. And
but so sorry, I think I'm getting a bit confused. So which spectral triple are you?
I started with a spectral triple
On
in the
singular
start.
from H?
No,
No.
AHD.
Huh?
AHD, any arbitrary.
Okay, so, oh, okay. And then you were taking that D. Okay.
Yeah. So what I did, so I started with AHD and I circled H to take as a first ingredient to quantize. Now I take the third ingredient and try to see how that sort of fits in this formalism of second quantized type. But the starting point is always AHD, no conditions whatsoever. Maybe there will be in a result later on, but at the moment it's just a spectral triple. So it applies for all cases. And then I will give the examples where we see what does it mean and so on. But in principle it's all there. And then, so this always gives a unitary, e to the ITD. And in fact, so it induces such an automorphism. And now the question is, can I realize this in a way that that I just described in terms of the wedge? So first of all, let's look at the first proposition, which is in this paper with Shamsuddin and Kohn. So such a combination of C is this Clifford algebra, with this automorphism depending on T is in R. So this is called the C-star dynamical system. So it's just name attached to this combination of a C-star algebra with a one-parameter group of automorphisms acting on the C-star. This is a one-parameter group of automorphisms. Just means that if I apply sigma t and sigma t prime, then the t's will add up. Okay.
So what is C?
C is this.
Oh,
It's this one. So.
oh yeah.
Yeah, it's a bit shorter. Let's see. But it's my C-star algebra that will play the. That's the only C-star algebra that will appear today. So that's why I call it C. And so if you have such a one-parameter group of automorphisms acting on a C-star algebra, you may be trying to find some trace that is compatible with this. Well, it's not really a trace, a state, I should say, which is still compatible with this one-parameter group. And these are called, in fact, this is an equilibrium state for the dynamics induced by this one parameter group. Let me explain what I mean. For any beta larger than 0, there is a so-called KMS beta state phi of this C-star dynamical system. And there is a unique. And this means, so KMS beta, this is another word, I mean, it's like an equilibrium. In this case, it will be like Gibbs states, which is phi. So it's like a trace, but not quite. So it wants to be a trace, but there is this automorphism intertwining. Okay, so this is actually the definition, well, the shortest definition, and also the not too precise definition, but I think this is sufficient for today. You have this KMS beta state, which if you, so a state is just a linear function which is positive, okay? So on my C-star algebra, A and B are in the C-star algebra. If I switch the order of B and A, it's not the same, but there is a sort of this sigma t kind of enters. And it enters not at time t, but at time imaginary time. So this means that there is an additional condition telling me that this formula should extend to the complex plane, or at least a portion of that. And so that's the more complicated version, that there is such a holomorphic extension for which the boundary values at this I beta satisfy that property. So there's an extension of this whole phi, including the t, which does that. But this I will not touch upon, but you can either read it in the paper or in the references, which there are plenty of, for KMS beta, in particular in the math literature. I mean, this is even less clear in the physics literature, even though it originates there. So it's very nicely defined for C-star algebras. So I think Brattelli Robinson is a good reference for these kind of things, these books. So we're going to try to write an explicit formula for phi. And we do this by taking a special choice for this complex structure, I, which we take to be I, D, D inverse. So it's like plus I on the positive eigenvalues, eigenspectrum of D, and it's going to be minus I on the negative eigenspectrum of D. So we're going to take a complex structure that is induced by the Dirac operator I started with. So the original D from AHD. So this means that if I look at e to the itd, it will not act as e to the itd, but it will act as e to the it absolute value of d. And this is of course very confusing because I wrote an I, and I have the I there as well, and my capital I changes the way I acts. So, but you should kind of bear with me that this is then the way it acts on VI. Yeah, so you get the absolute value instead. And this is good because if I evaluate this as t equals to I beta, it's going to be e to the minus beta d. And this is a very nice operator in the usual cases, trace class and so on. So proposition is that, first of all, I can use this situation to implement the automorphism with this e to the itd. And so that's first. Second, if exp minus beta d is trace class, then this phi beta, so the one appearing there, is something like some normalization. And then there is this wedge. Like this. So this thing here, this is an operator which, when properly normalized with this 1 over n, is called the density matrix. Or density operator. So it's now my representation of A times this density matrix, and then you take a trace. And it's like, this should be considered in physics at least, as an exponential of minus beta Hamiltonian. So that's the kind of Gibbs analog. So it's like trace of gamma IA and e to the minus beta Hamiltonian. So this is a Gibbs, so-called Gibbs state. The Hamiltonian tells you how to kind of, what to expect, where to expect the particle.
So what's that constant?
N is the trace of this thing.
Oh.
So the density matrix is this is combined, so it's normalized. So rho beta, and this is just a trace of this wedge in front without the gamma IA. So that actually this is a state. If I plug in 1, I get 1. So that's okay, so then let's see. So there's a few things we can do with this. So we have this situation where we have this equilibrium state. We have an explicit formula for that in terms of the D that we started with. So what we can try to compute, that we do in a theorem, is its entropy. So this is the von Neumann entropy, so it's the trace of rho beta log beta rho beta. So this is von Neumann, which I spelled, I noticed, with double M in my abstract. It should be with one M, of course. Is actually given by a so-called spectral action. And that's something that lives on spectral triples. It's a trace of a function of D. So S of rho beta you can compute to be the trace. So this trace is over the wedge, but this trace here is over H, the H I started with, of H beta D. So this is something that lives on spectral triples. Whereas the left-hand side is something about the quantum system. So you get back to the place you started with, and this H is very special. It's e to the minus x, and e is this formula. And this I need to explain, of course. I understand that.
So that is S beta or S of?
Sorry?
That is S beta, left hand side.
S of rho beta is what I called.
Yeah.
Yes, sure. Yeah. Yeah. Let's do it like this. So if you have a density matrix, then this is defined. Yeah. Thanks. Yeah, so let's spend a few words on entropy. So E, for instance, is the entropy of dividing a unit interval in two pieces. With size of ratio y. Okay, so since I assume you're not familiar with entropy at all.
Sorry, Walter. So what is E beta?
That's density matrix.
Oh, okay.
Rho. This is a rho, sorry.
Oh, okay.
This is supposed to be a rho. And here as well, so rho beta. It's my density matrix rho beta that I had over there.
And so for any, so how is the, so what is the one entropy defined for any system, dynamical system with a KMS state?
No, it's defined for density matrices. So such operators. And this is that happens to be the type 1 situation. So what you're talking about, it's a type 1 state which is represented by such a density matrix, where you can take traces. And so that's why the trace appears and not some kind of von Neumann trace. Yeah, I will explain this this entropy of the sizes in a moment, but let's first do something for entropy, at least that you have the idea what this is about. So entropy is like a notion, it's saying something about how much information you have about the system. And so let's give an example on C2, which is independent from what I was doing here. And let me call 1, I will call the vector 1, 0, and this is the vector 0, 1. Very fashionable these days. These are qubits, okay? Or at least these are still bits, but I allow any vector in here, and that will be called a qubit. So it's a combination of a 0 and a 1, and it can be arbitrary. So maybe you say it should be of norm 1, that's fair enough. So there's a few conditions maybe to make this a qubit, like probably this should hold. But then it's like I have some a superposition of a 0 bit and a 1 bit. That's the idea of course, quantum information nowadays. Quite fashionable. I don't know how this is here, but I think you have some faculties here that are quite active, I guess. And if I consider a state of a system, I can say, okay, let's take rho, and if I take my density matrix to be like this, then it projects onto the 0 bit. Okay, so this corresponds to the system in the state in the 0 state. The other one could also work. It's the same thing. It could also be in the 1 state, and you have a lower diagonal 1. But let's compute its entropy, okay, just to understand what this is going to do. So I have to take the trace of that rho over there, log rho. But there's all kinds of zeros, so that's for the logarithm not very good. But of course there is also a 0 in front. So by the way, note that what I'm doing is I apply functional calculus on the matrix rho using the logarithm and so on, but it's rather harmless because this rho is diagonal, or it can be diagonalized. So it's just 1 log 1 minus 0 log 0, which I view as 0, and this is viewed as 0 as well. Okay, so the entropy is 0, which means it's actually telling me that I have full information about the system. I know it is in the 0 state. The other extreme, where I don't know that, I take a combination of the two, rho being 1/2, 1/2, and now it's like half in the up, or in the 1, half in the 0. So let's do the computation again. So the entropy of this one, anyone, by the way, wants to Make a guess.
1? No.
What's proportional to 1? So it's log 2. You have to, of course, play with a logarithm of 1/2, which is not too difficult, and do that twice. So that cancels the minus. That's the most important thing. The log of 1/2 will be something like minus log 2. And that's crucial because it will then help to, and the 1/2 in front, that will add up to 1. So that's it. That's the computation. But the fact that it's 1/2 is crucial. So this is actually always positive, even though I put in a minus sign. Actually, I put the minus sign to make it positive. And actually, if you take t and 1 minus t as rho, then you would find something like it would go up like this. So this is actually the maximum. So the largest entropy you get when you have actually no information about which kind of actual state you are. So the 0 or the 1. Now I know absolutely nothing about where am I with my density matrix. In which state am I? I'm really half in between. And so that means that the entropy is largest. So that's more or less how you should think about entropy as a measure of the lack of information. Maybe this other one. So if you take a division of an interval in 2 pieces of ratio y, then my rho, so the second example, which is this thing, is rho is y, or let's take 1 over 1 plus y, and then y over 1 plus y. So this is the division. So ratio is now y of my this kind of division. So this is like this is the length of this this part, and the other one is the other way. Okay, and this should add up to 1, which it does by just looking at these two things. So this is what I mean when I say, okay, dividing the interval in 2 pieces with size ratio y. I'm talking about such a density matrix, and y is the parameter. Then actually the S of this row, this is what I called E of y, which you can compute. I mean, this formula is just a result of applying my rho log rho to that particular form of rho. It's another way of viewing this one as well, because it's very similar to this one. I just reparameterized this division. So it's similar but different. So that's the E of y I have over here, and it happens so that this is a universal object for all spectral triples. So AHD is arbitrary, except for the constraint for the trace of e to the minus beta d being finite. Okay, so that was in what I just erased. So that needs to be some summability should be in place. All right, so let's do some examples of this. That's also more or less the kind of the final things I will be doing. So maybe the most detailed one is the 2-point space again. The thing is with entropy is that it gets quickly rather difficult if you take complicated, or this spectral action is the same thing, but it's very easy for these kind of finite dimensional systems. So we do that again, 2 points. And the distance is as before. So I have this 1 over absolute value of c, which I call r. So the distance is 1 over c. Okay, so I just denoted this as r. And it grows inversely proportional to the c appearing in d. So for this, I can actually Now use this theorem to compute the entropy in terms of just D. Because, so my D is acting on a two-dimensional Hilbert space, C2. The wedge of that will already be much larger. So this quickly grows, and so for that you have to be a little bit careful. And the nice thing is then this D has this very nice behavior, because I know exactly its eigenvalue, so I can compute what it is. And so what you find is that if R goes to 0, or in other words C goes to infinity, then this is 0. And if this R goes to infinity, or in other words C goes to 0, then it's actually maximum. And in a plot it looks like this. Well, this is not very exciting. It's just increasing. But it means that entropy is increasing as the distance grows. And this is something that is a nice perspective, because as you may know, so if you think about what I just described about this, so order has lowest entropy. So order means I sit in a 0 state. And so that's... but that's not the most typical situation that will happen. As you know, I mean, chaos will quickly appear in life. So an entropy is only increasing. So it tends to increase. And so this is actually such a state as this one, or any kind of combination of these two, is much more likely to occur than this one. And in fact, you're driven into that by all kinds of disturbances or whatsoever. So the mantra in physics would be that entropy should be increasing. So that means that if you take that as a sort of a principle, it tells you something about these 2 points, what they want to do. So if you take the entropy to increase as some kind of input, then it means that these points tend to kind of get further and further away from each other. And this has been formulated, or can be formulated in terms of entropic force. And I think in the old days, well, maybe this applies here as well, but this kind of bunch of cords. But if you had a telephone with kind of the wire, which we don't have anymore, but that tends to kind of coil, which is increasing entropy, and it looks as if there is a secret force that wants it to kind of coil and to be completely knotted. But as this doesn't apply anymore, the idea is that it becomes more and more kind of complicated to unwire, and to the underlying principle is that the entropy forces it to be in such a state, the increase of entropy. And so this happens here as well. So you can actually define an entropic force of R, which is the derivative of this S, what I call S rho beta, but as a function of R in this case. And then maybe this in front. So that is more interesting, because that you can show it's actually can be computed. So also the formula, of course, can be computed easily, but this is entropy. But the entropic force is more interesting, because that tends to increase and then decrease. Yeah, so there's a desire for these 2 points, if they're a little bit away, to actually move much further away, and then it sort of stabilizes. There's no kind of need to move further and further, because then this kind of drops. And that's a nice interpretation of geometry in terms of such a principle. So this needs much more study. So this is an opening, and in fact this is not written anywhere, but it's just kind of some idea that is being developed. So it's an invitation also to think about these things. Let me give only say one kind of hint of a general structure, and then I will wrap up. So actually this h that appeared here, this function h, is actually much better than expected. It's a Laplace transform for some gt, which I will not write. It's not so important at this point. So this h, which is this of e to the minus x, is actually a Laplace transform. And this means you can use heat asymptotics. If I want to compute h of beta d and its trace in particular, because it means that e to the minus t d squared appears. And the trace of that, that's the heat operator, the trace of the heat operator is very well understood in many cases. So if you know this one asymptotically, known in many cases, like manifolds, also this combination of manifolds with C plus H all applies. So there, and also non-commutative spaces, there have been developments there as well. So that means then, if you know them, then the entropy can be computed in terms of them. And it's a surprise that what enters are coefficients. So k here is the same k as that enters there, which may run from, actually this is the t to the minus 2 that I had, or t to the minus d, or lambda to the d I think I wrote, that appeared in the Wiles formula. So that's the same kind of starting point. This S of rho beta is expressed in terms of gamma k's, their coefficients, which are proportional to the Riemann psi function. And that was quite surprising. So it's there's some kind of introduction of, and it's because of this function gt, which we know explicitly, that gives rise to these values of the Riemann psi, which is a product of the, as you may know, of the Riemann zeta with the gamma function. So then it means that, for instance, for C infinity of m, L2 dm, I can compute this, and that's actually as far as I will get, that this entropy will actually be C4, and then the volume of m, and then the second term I will write, and then I will stop writing in this case. So the first term you get in this expansion, in dimension 4 by the way, which is the, say, the most relevant if you think about physics, is the volume of m. The second one is the scalar curvature. And this is actually driving the dynamics of gravity. So it's the Einstein-Hilbert Lagrangian that describes general relativity. So it's giving you the in vacuum, because I didn't put any. I mean, if you would put some kind of some additional terms, then you would get it coupled to matter. But for now, this is sufficient, I think, for today also. So so that's it. I will end with a dictionary that should guide you a little bit what I was doing today. And I guess this is the most challenging day of the week, especially because I touch upon these physics, and tomorrow I will kind of go back again to more kind of, say, down-to-earth methods. So the spectral action is a trace of a function of d. So that lives here on the side of spectral triples. This is the world of non-commutative manifolds. If you want to quantize these, then the first thing we saw is that we replace the Hilbert space by the Clifford algebra, complexified Clifford algebra on this HR. D was giving rise to this these one parameter automorphisms coming from e to the ITD. A was driving these inner fluctuations, as we have seen. So that I haven't touched upon today, but it means that D will be replaced by another generator, which is D prime. So it kind of moves this group of one parameter group of automorphisms to another one, which is determined by this D prime coming from these inner fluctuations. And this is the entropy of a unique KMS state associated to this system. Yeah, and it gives me back the spectral action. So that's the sort of the analogy between the things. All right, that's it for today. So thanks. Yeah.
So questions. Okay, so since no one has questions, so yeah, I have a few questions. So just can you just repeat what you meant here? So roughly speaking, so what is meant by second quantization?
Yeah, so second quantization, maybe a first historical remark. So it's so the idea is that you want to. So why it's called second quantization is because it's so in quantum mechanics, there was already this notion of a Schrödinger equation. So you have a wave function, and that is sort of quantized already, but it's a single particle. And so you have to do another kind of type of quantization, which is this one, the second quantization, to move it into to something which allows for multi-particle states. And they will be in this fermionic Fock space. So this is how you should view it, that is sort of now the place where quantum field theories actually take place. So it's where particles, multiple particles can interact and merge into another one or collide. So where collision experiments are actually modeled, kind of, so the outcome will be computed in these kind of contexts. But this is the framework where this is supposed to take place, and second quantization is that step to kind of set the scene for where quantum field theory should be sort of defined, Fock space. Yeah. I don't know if this helps, but the notion second is more historical.
Yeah. So you started with a spectral triple, and you had so you've only written the bosonic part of the spectral action, right?
Yeah.
And then so can I so is it the fact that I should view that A is replaced by the Clifford algebra, or no?
No, it's more. No, I don't think you should find the spectral triple in here.
Okay.
That's not the idea.
Okay.
You replace it with something which is more appropriate for dealing with multi-particle states. Where I should also add that this is fermionic, because we took the fermionic Fock space. So it's like a quantization only of the fermions, and the sort of the algebra is still acting on the background as a classical transformation. So that's still why this is not a full theory, a full quantum theory. There are still a lot of steps to be taken to understand this passage. Here in D and D prime are just classical gauge fields. So there's no Fock space built on gauge fields. So in other words, on the algebra.
Yeah, sure.
As I understand from the lecture, do you suggest that the action functional of dynamical systems can be viewed as entropy of some KMS states, right?
Yeah. So, but the entropy. I mean, this is the side of the C-star dynamical system, and this is the spectral action for the spectral triple.
Yeah.
So that's how I kind of would like to separate.
Like in mechanics, we define action functionals, right?
Yeah.
Now you are trying to view that in terms of a entropy,
That's right, yeah,
in
yeah,
terms
yeah.
of the von Neumann entropy of some
Precisely.
states, right?
Yeah. So in particular, so this is an example with this 2-point space. There is a sort of the geometry that is driven. So it's like I would view this even as it's an action principle like a Lagrangian.
That's right.
Which would be this one, which it's sort of let's say maximized or something like this. That kind of idea. But one has to be a little bit careful, of course, because that's not what you usually do. You try to minimize. So there's a lot of thought.
Extremization.
Extremization, at least.
Yeah.
And but this is because, as you see, the entropy is. Well, let's look at this one. So, if you look at that entropy, these are the first terms in an asymptotic expansion.
Yeah.
They are the ones that you may recognize as action functionals or Lagrangians in physics.
And
But
these are all classical terms,
Classical terms, yeah.
Yeah.
But there are higher terms.
Okay.
This continues. I mean, this is an infinite series.
Okay.
It's asymptotic even. So I don't even know what S of rho does. And in fact, there are explicit formulas for the resummed version. So it's not even Borel summable. There's no kind of control of the summation here. But you can actually find formulas for this which are exact and not expounded in beta.
Okay.
And then you can wonder, okay, what does it mean, this entropy, as a principle that drives either my geometry or should it increase, whereas this tends to decrease because you want to minimize this, right, in physics, typically. You want to
That's right.
minimize that action functional. But I think there's a competition between the full expansion and these individual terms.
Okay. So it's very interesting and like opens up a new paradigm for like visualizing dynamical systems.
Yeah, exactly. And it's so this is also very close to developments in physics, which are about using this kind of entropy to have so the appearance of geometry. So this is actually in line with that. So I try to also develop this. Yeah, that's.
Okay, thanks.
Thanks.
Okay, so my question is, does this asymptotics is independent of inner fluctuation? That's my just intuitive guess. I mean, fluctuating by inner doesn't change this asymptotic terms. Is that true? in general?
Well, they depend on the fluctuations.
Okay, so
But
for
I didn't
some inner fluctuation, it can also change the coefficient of the asymptotics.
Here, maybe if I write, because I didn't write any fluctuations, but there will be a term like this.
Uh-huh. Okay.
Like if you fluctuate this, then naively speaking, this will be electrodynamics.
Okay.
So dm will couple to a field, which has like a dynamical, so a Lagrangian for that's like a U1 gauge field or the bosonic part of electrodynamics with a C0, and this will be scale invariant.
So that means, I mean, they can in general change the coefficients.
Yeah.
Okay.
Well, even the whole value. So these are integrals, right? So these are additional terms that would couple this to the fields.
Okay.
C0, C2, and C4 are constants one can compute. It's
Okay.
like this volume of. So this is of course very similar. This volume appears because of Wiles' law, as we explained in the beginning. There was also this volume. So and it is the leading term that has that behavior.
Thank you.
Yeah.
Right. So, are there any more questions? Okay. So if not, let's thank Walter again. So we meet tomorrow again at 4:15. So we have some sweets outside.